Welcome to another National Training Center Tech Byte, liquid immersed transformer insulating fluid. Specifically, the interpretation of gases generated by the decomposition of mineral oil. This is the general introduction. Tech Bytes are quick videos that will be from 3 to 8 minutes in duration to cover a very specific topic or issue associated with the world of electricity. This Tech Byte topic is associated with insulating fluid used in liquid-filled transformers. More specifically, an introduction to the interpretation of gases generated in mineral oil. This training is derived primarily from IEEE C57.104-2008, IEEE Guide for the Interpretation of Gases Generated in Oil-Immersed Transformers. This training must be applied within the context of the IEEE standard and is meant entirely to act as a quick explanation of one or more specific gases and a refresher to the experienced engineer or technician. Mineral oil decomposition. Mineral oil fluids used in transformers are mixtures of many different hydrocarbon molecules, and the decomposition process for these hydrocarbons in thermal or electrical faults are complex. The fundamental steps are the breaking of the carbon-hydrogen and carbon-carbon bonds. Active hydrogen atoms and hydrocarbon fragments are formed and combine with each other to form gases, molecular hydrogen, methane, ethane, etc., or they can recombine to form new condensable molecules. Further decomposition and rearrangement process lead to the formation of products such as ethylene and acetylene, and an extreme to modestly hydrogenated carbon in particulate form. Hydrogenated carbon is carbon that has been combined with hydrogen to form solid particulate. All transformers generate gases to some extent at normal operating temperatures, but occasionally a gas generating abnormality does occur with an operating transformer, such as a local or general overheating, dielectric problems, or a combination of these. In electrical equipment, these abnormalities are called faults. The three types we are concerned with are thermal, partial discharge, and arcing faults. Internal faults in oil produce the gaseous byproducts hydrogen, methane, acetylene, ethylene, and ethane. When cellulose is involved, the faults can additionally produce carbon monoxide and carbon dioxide, CO and CO2 respectively. So how does this work in our equipment application? Each of these types of fault produces certain gases that are generally combustible. The total of all combustible gases may indicate the existence of any one or a combination of thermal, electrical, or partial discharge faults. Certain combinations of each of these separate gases determined by chromatography are unique for different fault temperatures. Also, the ratios of certain key gases have been found to suggest fault types. Interpretation by the individual gases can become difficult when there's more than one fault or when one type of fault progresses to another type, such as an electrical problem developing from a thermal one. Key gases are, in fact, gases generated in oil-filled transformers that can be used for a qualitative determination of fault types, based on which gases are typical or predominant at various temperatures. Attempts to assign greater significance to gas than justified by the natural variability of the generating and measuring events themselves can lead to gross errors in interpretation. However, in spite of this, these gas generating mechanisms are the only existing basis for the analytical rules and procedures developed in the IEEE Guide. In fact, it is known that some transformers continue to operate for many years in spite of above average rates of gas generation. The best use of the gas analysis and oil analysis is as a condition-based tool. It should not be used as the sole data point to determine transformer status. We must use additional oil monitoring, and when the issues we are seeing are significant, other testing measures offline to truly determine the condition of the transformer. Oil analysis and gas evaluation is one of many tools. Establishing a reference point for gas concentration in new or repaired transformers and following this with a routine monitoring program is a key element in the application of gas analysis. Any owner with liquid-filled transformers should own a current copy of the IEEE standards associated with insulating fluids. Monitoring and health and serviceability of a transformer must be done on a routine basis and can start anytime. It is not just for new units. Generally, daily or weekly sampling is recommended after startup, followed by monthly or longer intervals. Routine sampling intervals may vary depending on application and individual system requirements. ppm is parts per million, and also referred to as microliter per liter. They equate to the same. Here we will be using ppm. The limits here are for condition 1 as defined by IEEE standard C57.104. All of the gases listed contribute to the total dissolved combustible gas, or TDCG, except for carbon dioxide. Hydrogen, methane, ethane, ethylene, acetylene, and carbon monoxide are all our combustible gases we look at. They have various independent limits, but the TDCG overall has a limit of 720 parts per million, and once it gets over that, is no longer considered condition 1. TDCG below this level indicates the transformer is operating satisfactorily. Any individual combustible gas exceeding specified levels should have prompt additional investigation, and that investigation will vary. Again, we refer back to our IEEE standard for proposed actions. This concludes this introduction. Be looking for short tech bites on all of the gases and combinations of gases. We will be putting out an advanced analysis tech bite to cover condition evaluations and actions. Finally, full training towards CEUs will be available in the future with a trainee guide and exams. This concludes our training. Look for additional tech bites. Subscribe to be notified as the information is added. And thank you for your time, and I hope this was very helpful.